Hello everyone, welcome back. So we are going to continue our discussion on Thevenin and Norton theorem, and now we are going to introduce what will happen if we have a dependent source and we have to determine or apply Norton and Thevenin theorem. So here we have considered one example. So where we have a voltage dependent voltage source which is dependent on this voltage Vx. Okay, so in order to determine or apply Thevenin Norton theorem, as the question states that we have to determine this current IL, to determine the current IL using both Norton and Thevenin theorem. So as per Norton and Thevenin theorem, what we know is any complex linear bilateral network can be converted into a simpler network containing a voltage source and a series resistance in case of Thevenin circuit, and in case of Norton circuit it is represented by a current source and a parallel resistance. So we have to convert this circuit into this format and this format. So first let us determine VTH. So for determining VTH, let us redraw the circuit again. So this is our circuit. So now in order to determine VTH, what we have to do, we have to remove the load and we have to determine the voltage across this terminal. That means we have to determine VTH here. Okay. So in order to determine VTH, so we have 2 ampere here current here, and this is our remaining branch. So since this terminal is open, so whatever current is flowing through this loop will be the only current in this circuit. So in order to we can write down the KVL, we can directly write down this voltage Vx, or we can write it like this: Vx minus 2 divided by 2. This current is nothing but 2 ampere. So from here we can determine the value of Vx, which will come out to be 6 volt. So now what we can do, we can determine the value of VTH. So for determining the value of VTH, what we can do is we can consider the outer loop, and if you write down the KVL equation, then it will contain the value of VTH. Okay, so to do it, so we can do it by suppose 2 volt minus 2 into I1, then 1 into I1 minus 4Vx, then minus VTH equals to 0. Or in place of writing this to drop, we can also start from this voltage and write it as Vx minus this voltage drop. Then we have another voltage drop here, so that will be minus of minus 4Vx, and then we have this voltage drop which will be minus of VTH equals to 0. So just by writing down only voltage drops. So since we do not have any current in this path, so this will get neglected. So what we have here is 5 times of Vx equals to VTH, and we already have the value of Vx, so therefore VTH equals to 5 into 6 equals to 30 volt. Okay, so I guess this is understood. Now next what we have to do is we have to determine the value of ISC. So let's see what will be the value of ISC. So for determining the value of ISC, what we have to do is we have to remove the load, and we have to put a short circuit here and then determine the value of current. So this is a short circuit. So now here we have one node, so we can write down the nodal analysis here. So it will be Vx minus 2 volt divided by 2. Then this is in the opposite direction because we consider in nodal analysis current is moving out. So this will be plus of minus 2. Then we have plus of Vx. This will be plus 4Vx divided by 1 equals to 0. So from here we can solve for Vx. So Vx is 0.545 volt. Now the value of ISC current is nothing but this current. So this current will be given by Vx plus 4Vx divided by 1. So which is nothing but 5 into 0.545 equals to 2.73 ampere, right? Now in order to determine RTH or RN, if we draw the circuit diagram, then it should contain only resistances, right? And all the sources should be replaced by the indirect resistance. But here in this case we have a dependent source, so we cannot eliminate this dependent source here. So in order to determine RTH or RN, we have to use simple Ohm's law. That means, suppose if you consider this is our load resistance where we are going to determine the value of VTH, RTH, ISC. So the value of RTH can be given by VTH divided by ISC, which is also equals to RN, right? So this value will be 30 divided by 2.73, which will come out to be 10.98 ohm. So now if you put this in the Thevenin circuit, this value was, we had obtained VTH as 30 volt and RTH as 10.98, and this was our 10. So the value of current IL is 30 divided by 10.98 plus 10, which will come out to be 1.43 ampere. Similarly, you can also determine it from this circuit, Norton circuit. So the value of IL equals to this RN value is 10.98, value of RL is 10 ohm, and this is 2. So we have obtained 2.73 ampere. So this will be 10.98 divided by 10.98 plus 10 multiplied by 2.73, which will come out to be 1.43 ampere. Okay, so this is how we determine Thevenin or Norton equivalent circuit, or we can solve using Thevenin and Norton theorem. So now let us see whether whatever we have determined is correct or not by looking at the simulation results. So as you can see here, the circuit contains one second. Okay, so the circuit contains a 2 volt, 2 ohm, this is 2 ampere. Then we have 1 ohm resistor, this 1 ohm resistor. Then we have a voltage dependent voltage source. This is a voltage dependent voltage source. So this is the source, negative positive terminal, right? And then we have positive terminal is connected to this point Vx, and negative is connected to the ground. So the circuit is complete now. So when we run this, we are obtaining the value of RL to be 1.429, and the same circuit when we applied with Thevenin and Norton equivalent circuit, then also we are getting the same answer. Okay, so that means whatever you determine is correct, and it is proved by the simulation results. Okay, so this is how we can determine any circuit containing a dependent source, and we can determine the equivalent Thevenin and Norton circuits, and we can determine the current using Thevenin Norton theorem. So similarly, like this, we can solve any numerical which will contain dependent sources. Okay, so I hope this is clear for you. So if you have any doubt, you can put it in the comment section. We will try to solve those numericals again in our future classes. So thank you for joining, and see you in the next class.